are doing, beta, in continuation? Work done we have already discussed, and we know about the mechanical energy also. When we talk about the mechanical energy, now mechanical energy that can be of two types. One is kinetic energy, another is potential energy. So I can divide mechanical energy into kinetic energy as well as the potential energy, as we have discussed in the previous lecture. So firstly, let us take now one by one both the energies. We have to take kinetic as well as potential. So we are starting with the kinetic energy in this lecture. So what it is, kinetic energy, it is defined as the energy of a body by virtue of its motion. Like if you are having a ball is coming with motion and it is coming and hitting you, you can feel some work is done by that ball. So by virtue of its motion, because it was in motion and because of its motion, it is possessing some energy. So you can say that kinetic energy is defined as the energy possessed by a body by virtue of its motion. Energy possessed by a body. And of course, we can measure kinetic energy by its work done. Like what work it is doing. So work done will get converted into the form of energy. So if a ball is coming, moving cricket ball is coming, supposingly it is possessing the kinetic energy, and when it is hitting, so that it can move some another body. So that work done we can find, and then we can just relate the kinetic energy and the work done. To derive the expression for the kinetic energy. So for that, if you wish, you can make a simple diagram with you. That is, if you are having a body here, you are applying the force F, and as a result, you are able to move the body. This is, of course, the distance is always taken from the central point. It is able to move the body through this position A to position C. So what I'm saying is that and of course you can take the mass is M, mass of the body is M, and your body is moving with velocity U because you are applying the force F, but need to understand that if we are saying that V is the final velocity, S is the displacement, then by the definition of work done, we say work done, it is equals to force into displacement. Now we are taking force and displacement, both are in the same direction. I am moving from position A to position B along the horizontal line. So theta is 0, so work done will be having the maximum value. So you will be saying work done, it is equals to F into S. But if you are saying its velocity is getting changed from U to V, it means it is going to have some acceleration A. So by the knowledge of Newton's second law, you can write F, it is equals to M into A, and multiplied with the displacement. So work done, it is coming out to be MA into S. You may call it as equation number 1. So this is again otherwise known to you by the definition of work done, and by using the Newton's second law, you should be able to write the force and displacement you have to suppose in your example, whatever example you want to take. Now third equation. By the using the third equation, if you write V square, it is equals to U square plus 2AS. From here you can find the value of A, or you can find the value of AS, which is coming out to be 1 by 2 V square minus U square. So if you put this value here in the first equation, that was M into AS. So in place of AS, I am putting the value half V square minus U square. So if you take that initially the body is not having any velocity, initially the body is at rest, then your U will become equals to 0, and you can write kinetic energy, it is equals to half mv square. So this is the expression with you for the kinetic energy. So mathematically you can write kinetic energy, it is equals to half mv square if initially the body is at rest. So because of the velocity v, the kinetic energy will get changed if you are having a given body of mass m. So this formula you need to keep in mind with you, and of course derivation can be asked as a direct question. The points which you need to note is that kinetic energy is directly proportional to the mass of the body and directly proportional to the square of velocity of the body. So you can be asked with the conceptual questions like mass of a body is doubled and velocity is becoming half, then what will happen to the kinetic energy? So you should be able to do those type of questions. Of course, they may ask you to write the kinetic energy in terms of linear momentum, because we have discussed linear momentum in laws of motion. Then you should be able to write that it is equals to p square upon 2m, because if you linear momentum is m into v, so here you are getting half mv square. So on that also the questions can be framed, like I'm saying that your kinetic energy, that is equals to half mv square. So if you multiply and divide by m, it will not make any difference. So you can write half m square v square upon m, and m is what? That is m into v is what? That is linear momentum. So you can write p square upon 2m. So you can be asked with the questions related to your this kinetic energy and linear, what is happening if I am changing the linear momentum. So those type of conceptual questions can be asked with this formula also. You can keep in mind, you can directly use or you can solve at that time. Of course, the second point you have to notice that kinetic energy is always positive. Because mass is positive, now the question can be asked why kinetic energy is always positive, because even if velocity is negative, square of the velocity will become positive. So you can say kinetic energy is always positive. Of course, kinetic energy is a scalar quantity because it is equals to work done, and work done is a scalar quantity. So reason also should be clear for everything. Whatever you write, you should know the reason. Of course, you can use the term speed in terms of velocity. That is also equally correct, because it is not going to make, if you are given with speed, then also you can find the kinetic energy. It means for a given direction, they may mention the word speed. You should not get confused with the things. So these are the points about the kinetic energy which you have to keep in your mind. Of course, units and dimensions are same as that of work done. So it means you will be measuring the kinetic energy in joule or erg as per the SI or CGS system of units, and dimensional formula is also same, that is mL2T minus 2. So for these quantities you may be asked with the questions on the dimensions also. That also should be clear in your mind. Very important theorem with you, that is termed as work energy theorem. So the same diagram which we have discussed previously, that same diagram is to be made. It means you are having the body, it is actually I can say it is the repetition with you, that if I am having the body is of mass m and it is moving through the displacement s by applying the force F, then this is the displacement s. Then you can write it same way. Now initial velocity we are taking u, and that has to be u itself, and final velocity is v. And by using the third equation, if you are multiplying with m by 2 on both the sides, you are getting half mv square minus half m square, it is equals to mas. So you can write it as ma is force applied and s is the displacement. Then this fs can be written as work done, or this is the final kinetic energy, half mv square, and half mu square is the initial kinetic energy. So you can write kinetic energy final minus kinetic energy initial, that is equals to work done. This relation itself is known as work energy theorem. So it means change in the kinetic energy, it is equals to work done on it by the net force. Of course, here again we are talking about the constant force. I am applying the constant force. But if I talk about the variable thing with you, then again you can prove it by the integration method also. You can prove the work energy theorem firstly by the third equation of motion using, it's very simple, all the steps are quite simple, all the supposition whatever we have done earlier. And method with you is, if I am having a variable force, then I can go with the integration method also. So for that you will be using, this is important beta, you have to note in the question whether they are asking you work done by a constant force or work done by a variable force. Similarly, work energy theorem for constant force or for variable force, you have to go by different methods, and if the question is silent about it, then it is your choice. You can do by any of these two methods, whatever you feel comfortable. If they are asked you, they are not mentioning, they are simply asking state and prove work energy theorem for 2 marks, then you can go with any of the methods. Statement is already clear, work energy theorems, it states that work done it is equals to change in kinetic energy. So now if kinetic energy is given by half mv square, if you differentiate both sides with respect to the time, I can write it as dk by dt. And on the right hand side, I can write dt of half mv square. Now half is constant, m is constant. Now derivative of v square will be equals to twice of v. So when you write it twice of v, then 2 and 2 will get cancelled and you are left with this. You can write equation as 2v dv because velocity is changing. If I am writing d by dt of x square, then it is equals to 2x. Now x is a not variable. Now here v is variable. So when you are writing here d v square, it will be equals to 2v into dv by dt. Now this you can write in terms of the force, because dv by dt is what? If I multiply it with m dv by dt is the force. And so you should be able to write dk, it is coming out to be f into dx. If the position is changing, then you can take the integration to find the change in kinetic energy from initial position to final position xi to xf. Kinetic energy is changing from ki to kf, and then you can find it by the integration method and you are able to get that change in kinetic energy, it is equals to work done, because work done can be given as integral of f dx. This formula you are already aware, so you need to work it out and you have to prove it that the change in kinetic energy, it is equals to work done. So this you need to take care. Now this was all about the kinetic energy. Now if we talk about the potential energy. Potential energy, it is defined as the energy of a body by virtue of its position. It means I am stretching the body, I may have a spring. Now this is the diagram of a spring. You may have a rubber which you are stretching. When you stretch and when you release, then what happens? When you release, then force is coming this way. When you are stretching, it means you are displacement and force both are in the outward direction. And when you release, then it gets compressed. Spring is getting compressed. And due to that, you can say the energy which is possessed in the spring, that is elastic potential energy. But if you are having a body you are raising against the gravitational force, then we will be talking about the gravitational potential energy. So it is defined as the energy of a body by virtue of its position or configuration. By position, if it is, we are calling it as gravitational potential energy. If it is because of the configuration, then we call it as elastic potential energy. So these both the energies are there in your syllabus: gravitational potential energy and the elastic potential energy. So you have to study in detail about that, about the gravitational potential energy as well as the elastic potential energy. Gravitational potential energy with you first, which is because of its position. Now, if you are having a box of mass m is kept on the surface of earth and it is being raised to a height h. When it is being raised to a height h, then what happens? It is you are working, of course, against the gravitational force. But your force applied and your displacement of the body, they both are in the same direction. So work done will be given by the force which is equal in magnitude to the gravitational force, and gravitational force is acting downward direction, that is mg. So magnitude of your applied force, it is equals to the gravitational force mg, and h is the height. So work done which is getting stored in this body when you are raising it through the height h, that is equals to mg h. So this is a simple derivation with you for the gravitational potential energy. Of course, it is also a scalar quantity, but if you take the work done by the gravitational force, then you will be getting the negative sign. So this can have the positive or negative sign depending upon whether the work done is positive or the work done is negative. Now what it is, if I go straight to the height h, or I take the body firstly here in between, then I move, or then I reach this height, it has been found that your potential energy, it is remaining the same, which is equals to mgh. So it is independent of the path followed. So this is, you have to note that potential energy is path independent. So it depends only upon the net height by which you are raising the body. And if you take the body up to a height h and then bring it down, work done in the upward direction is mgh gained by the body potential energy. And when you are bringing it down, then potential energy which is lost by the body is minus mgh. So total potential energy in the whole round, you can say complete round, that is equals to 0. And this is the proof for saying that gravitational force is a conservative force. So the forces, we can say whether they are conservative or they are non-conservative on the basis of whether the work done on the round trip, it is equals to 0 or it is not equals to 0. If work done, and it means you are starting from a point and you are reaching at the same point. Like if I am starting from here and I am reaching here, from A to B I am moving, and then I move from B to A. I'm completing one complete circle, complete round, I can say. Then work done in the cyclic process is 0. Then such a force which is used in moving the body, that is termed as the conservative force. So work done by the conservative force, it depends only on the endpoints. Like when you are raising the body, so gravitational is also termed as the conservative force. If someone is asking you to prove that gravitational force is conservative force, then the previous slide you have to explain that will work as the proof for it. And if you have to define, then of course work done by this force in closed path is 0. Similarly, we will be proving that the spring force is also conservative. Even your electrostatic force is also conservative. So all these things we will be proving in the coming slides. So you should be able to differentiate between the conservative and non-conservative force. So if the work done by the force is in the closed path is not zero, then this force will be termed as non-conservative force. It means it depends upon the path which is followed. So frictional force is an example of non-conservative force. Similarly, when we talk about liquids, we will discuss that your viscous force, viscosity is also a non-conservative force. So you have to keep things up to this conservative and non-conservative forces, and thank you everyone. Keep things up to this.